Okay, so we are still discussing the integrals. I should better say the indefinite integral. Now, last time we saw the definition. Okay, so we assume we have a function f which is continuous. On some interval, and we define then delta x to be b minus a over n, and we define a sequence xi to be a plus I times delta x, where our I is between 0 and n, and we choose sample points xi star in the xi's interval. So overall, we choose n of them. And using this notation, last time we have defined the so-called definite integral from a to b of f of x dx to be the following limit. So the limit n tends to infinity, and then the sum I from 1 to n, f evaluated at the I sample point times delta x. Okay, so this is the definition we have seen last time, and I also spent some time in order to motivate the definition. So we saw already that in case where f is larger or equal than 0, a is smaller or equal than b, what we essentially get here is an area. But as I have explained, so essentially we define the area like this. So we have to define the area by this limit here, and this is just another notation for the area. So in order to compute areas, we are naturally led to consider such limits. And we have also seen another example coming from physics, namely if we are interested in order to find out the distance traveled by some object where the velocity is, of course, if the velocity is constant, it's trivial, but if the velocity is not constant, we will also naturally encounter such limits. So it makes sense to give those limits a name, and that's the name which we chose. Now, last time I showed you already some examples looking at some specific functions f, and we tried to evaluate this limit, and we saw this actually not a very easy task. So depending on the function, even for quite simple functions we saw last time, like if the function is the cosine of x, the limit here can be get quite complicated. So what we essentially want to do today is we want to find a better tool to evaluate this limit here, or in other words, a better tool to compute the definite integral. Now, maybe I should show you some more examples. Like this, of course, is a very easy one. Last time we saw already how to compute, for instance, on this interval using the definition. Okay, we plug everything in, we encounter a sum, which in this case is very easy, more or less the sum over I of I, which we can sum up, and because we can sum it up, we can compute the limit. But actually, if you have such an easy function, it's easier. It's maybe much quicker to use the area interpretation. So just for this almost trivial example. Okay, so you see that, okay, this is 1 here. So we have here 1, 2, 3, and our function looks like this here. And you see what we have to compute, as I have explained last time. So this function is not non-negative on the whole interval. So what we get is not really the area, but so-called net area. So we have here this area where this area is counted positive, and we have this area where this area is counted negative. So you see that since these are just two rectangles, so in this case it's very easy to compute the integral. Okay, so you see that from this one you have times, and from this one you have okay, so 4/2, 3/2. Okay, so in this case it's very easy to compute the integral. It's better to use the area interpretation instead of using this definition here. Now, maybe this example is a little bit too trivial, but if you look at a slightly more complicated example, okay, so for instance, if you are asked to compute this integral, the integral from 0 to 2, and then the square root of 1 minus x minus 1 squared dx. Okay, of course, one possible way to do this would be, okay, you go into the details. So you write this as a limit n tends to infinity, and then sum I from 1 to n. For instance, let's choose the left endpoints of every interval as sample points. Then we have this function here, 1 minus, and for x we plug in. So our delta here is, delta x is 2 to the n. So we have 2 to the n, 2I over n minus 1 square, and times delta x, so you have 2 over 2 over n, and you have to compute this limit. Now this is not easy. Okay, so you see from this expression, you can try a little bit around, but this is not easy to evaluate this limit. Okay, but the essential thing is we recognize that this is an area. Okay, because you see that what we have to compute here, if we use the area interpretation, is just the area of one part of so here where you have y is larger or equal to 0. So if you plot this, okay, x, y, and you have here 1, and here you have 2. So what you have is you have just the upper semicircle with the center 1 and 0, and radius is 1. And what we have to do is we have to, by the area interpretation of this integral, we have to compute the area of this semicircle here, something which is trivial. So by looking at the integral using this interpretation, you see that you can immediately come up with the answer, whereas computing this limit would be rather tedious. And also we will today learn, okay, how to evaluate we will learn a better method to evaluate a definite integral, not by going into the details in evaluating such a limit. But for instance, for this integral, this new method we will learn, it will not be very helpful. So this is still, of course, the quickest one. So you should always, whenever you have integral to solve, you should always, because we will learn many rules afterwards, we will spend quite a lot of time in order to learn many rules in order to evaluate definite integrals, and but you should always keep in mind that maybe the most easiest way to solve an integral is to interpret it suitable as an area. Okay, so this is another example. Now let's look at the final one, one which I mentioned already last time. So last time I showed you, okay, if we are interested in this integral. Okay, so if you just know this definition here of the integral and you go into the details, so you see this is the limit as n tends to infinity. So for instance, using right endpoints, we have to evaluate this at the delta x is 1 over n, so you have 1 over 1 plus I over n, and then you multiply everything with 1 over n. So I showed you last time already, okay, this essentially leads to a limit as n tends to infinity, which has the form 1 over n plus 1 plus 1 over n plus 2 plus and so on plus 1 over n plus n. So you have overall n addends here in this sum. And you see here, this is not so easy to evaluate this limit. Okay, so even for this, as I have explained last time, even for this easy function, okay, just by directly referring to the definition of the definite integral, it would not be easy to evaluate it. Okay, I already pointed out last time, and this is quite essential, that this limit is not equal to 0. Okay, some students tend to believe that, okay, because every factor here, so every term tends to 0, the whole limit will tend to 0. It's not true. The reason is the reason why this is not true to look at this sum term by term and evaluate the limits and compute a limit like this is because the number of terms is increasing as n is increasing. So we will see today we will learn today a completely different way to evaluate this limit, and we will see this limit actually is ln of 2. I should maybe emphasize. Once we have found a different way to compute this integral, okay, we will get a proof of this. But I should maybe emphasize that it's not really necessary to use the theory of integration to evaluate such a limit. You can also try to find another way. But it's not so easy to evaluate this limit. So you see that even for this easy function here, 1 over x, the limit here in the definition of the definite integral can become rather complicated. And so you can imagine that we certainly need some better tool. I mean, better than evaluating such a better tool for evaluating such limits in order to compute such expressions. Otherwise, the task of integration would be rather complicated. Okay, so of course, since for this integral, okay, we are so far not able to compute the limit. It's because this is my claim. I haven't proved this. Okay, the only way we have in order to compute such integrals is really going into the definition. And any question? The only way of computing such an integral is you really go into the definition, you do it numerically. So you choose an n, and you evaluate this sum for n large enough, and you will get an approximation of this integral. But as I have shown you last time, okay, I showed you last time a table where I have done this, such a numerical approximation of some given integral for certain n up to n is equal to 1,000, and we saw from this table that the convergence, the speed of convergence, so the speed of convergence of this number to the integral seems to be rather slow. Okay, so we saw last time that we saw an example where we computed n, where we used n is equal to 1,000, so you have to do already quite a lot of computations, but the precision which we obtained for the integral from 0 to 1 x squared dx was just 1 or 2 digits. Now, this is something, as I have explained also last time, which is essentially a problem for many integrals. So if you just use the Riemann sum in order to approximate the integral, okay, you have to make n very large in order to get a good approximation. But if you choose n very large, you have to do lots of computations, so you will have many computation errors. This is the first thing. The second thing is, if you use the Riemann sum in order to approximate the integral, you still have here a freedom in choosing the sample points. Okay, so the natural question arises, okay, what is a good choice for the sample points? Okay, so which sample points to choose such that the speeds, that the approximation, if you fix n, you can choose different. You still have different choices for the sample points. So what is the best choice such that the error is getting as small as possible? Now, for this example here, let's maybe look at this problem. So using this example here, looks like this. Okay, so what we do is we divide the interval into subintervals. So for instance, like this. Okay, now in every subinterval we can choose a sample point, and you see from if the function is like this here, so this is of course this is a special case because this function is decreasing. It seems that the best choice for the sample points, because what you do is you approximate this area here by the area of a rectangle. Now, if you choose a sample point, the midpoint, okay, so you see then this here is the rectangle. So you are going to approximate the area on this interval below this function by the area of this rectangle here. And you see that if the function is decreasing, it seems to be the best to choose the sample point to be the midpoint. Okay, because you see that you make here some, if you look at this part here, you underestimate the area, and here you overestimate the area. So the average should be quite a good approximation. And essentially, this using the midpoint should be much better than, for this example, than choosing, for instance, left or right endpoint, because then you make a rather large error. So this is one of the simple approximation rules, which in our textbook is called, or which is commonly called the midpoint rule. Okay, so here you approximate the integral. So we use the most simplest idea in order to approximate the integral. We use a Riemann sum, because that's the definition, as a sum I from 1 to n, f of xi star delta x. But for xi star, here you use the special choice xi minus 1 plus xi half. So you choose the midpoint of the i's interval. And the resulting rule to approximate a given integral is called the midpoint rule. And we will later on, indeed, we will prove that from all the possible choices for the sample sequence, this is the best approximation you can achieve, if you fix the n, of course. Now, I've explained here why this is, for instance, much better than choosing left or right endpoints. But of course, you could object. You could say this function is very special. It's decreasing. Okay, for increasing function, I believe it. Okay, for a decreasing function, I believe it. But for a general function, okay, this might not be the best choice. But for a general function, because you can assume that the n is very large, so you divide. If the function does not behave too badly, okay, it will on every interval, okay, it will be either decreasing or increasing or constant. Constant is in case of constant, you can choose any point as sample point, and you will get a good approximation. So you can choose the midpoint. But if n is very large, so on a small interval, if the function does not behave locally too badly, okay, the function should be either increasing or decreasing. And from this heuristic here, you then understand why choosing the midpoint here is the best choice of the sample sequence. Okay, so that's why we emphasize this rule here with this special choice of the sample sequence. And you can use this now in order to approximate the integral, our given integral here. So the integral from 1 to 2 of 1 over x dx. Now, for instance, what I choose here is I choose the midpoint rule, and I choose 5 sample points. So 1 over xi star delta x. So what I choose is here this sample sequence. And if I compute here this value, then what I get is 0.691908. And if you compare this with my claim, namely that this is ln of 2, so you see that you have already roughly those 2 digits are correct. If you would choose of course, this is not convincing if you just choose one sample point, but if you would evaluate the same for sample points, for a sample point sequence where you use either left or right endpoints, and you compare it with the true value, we will see indeed this choosing the midpoints as of every interval as sample points is the best choice. Okay, so but as I have explained previously, whenever you have a numerical numerical method in order to approximate some integral, what you certainly need in order that such a numerical method has some worth is you need some information about the error. So we still have to, we will later on prove an estimate at least for the error. And using this estimate, if you have such an estimate, this numerical method will make more sense. Because if you do not have an error estimate, the only thing you can do is you can make the n larger and larger. You compute the corresponding sums here. And because you do not know, actually, in most of the cases, of course, you do not know what the, or in all cases, you do not know what the real value is. Otherwise, you would not use this method. So you still have to know when to stop, for instance. If you make the n larger and larger, you still want to know, okay, when do you have to stop that you get a certain precision? Okay, for instance, you want to have that the numerical value you get is not too far away from the real value, and you have an error bound. For instance, you wanna have that the first 5 digits are correct. Now, I explained to you already that if you have no error estimate, no information about the error at all, okay, a numerical method normally is not very helpful, but you still can do the computations, and we quite often use the rule that all the digits which do not change anymore, they are correct. And like this, you can decide when you are going to stop in using the midpoint rule. But this should just illustrate, okay, for many integrals at the moment, using this definition here, the only way we can compute the integral is doing approximation. Because we saw, once more, even for easy examples, evaluating these limits is either not very easy or it's not possible. For instance, in case of this example. Okay, so maybe I write a definition of the integral once more. Okay, now, of course, the most easiest rule is if you interchange upper and lower limit, what will happen to the integral? If you look at the definition, now, if you really interchange, the only thing which will change is the delta x, and it will change from positive to negative. So you will get that the integral is minus the integral from b to a f of x dx. Okay, so that's the first rule we get, just from the definition. So the reason is because the delta x here will change, because delta x is b minus a over n in this case. And here you have a minus b over n. So you have, compared to this delta x, here you have the minus delta x. And another simple rule is, okay, so if you evaluate this, if you want to evaluate this integral, you see that delta x is equal to 0. So what you have is 0, just from the definition. Now, some more rules, which you also see immediately from the definition, is that the integral from a to b c dx is c times b minus a. So you, because you see that this is c here, you can take it out. The rest just sums up to b minus a. Now the integral from a to b of f of x plus g of x dx is equal to the integral of a to b f of x dx plus integral from a to b g of x dx. So this is essentially the rule that the limit of a sum is the sum of the limits, and the integral of from a to b c times f of x dx is equal to c times the integral from a to b f of x dx. It's essentially the rule that the limit of the constant times the function is constant times the limit. So all those rules here are trivial. Follow immediately from the definition. Now you see already from those two you get the consequence, namely if you look at this here, the integral from a to b f of x minus g of x dx, because you can write this as the integral here you do not have to go back to the definition, because you can write this as the integral f of x plus minus 1 g of x dx. So you use this rule, and you get that this is equal to the integral from a to b f of x d of x minus the integral a to b g of x d of x. Of course, like rules like this or this here, you can easily get a heuristic proof in case where f of x and g of x are both non-negative, a is smaller or equal than b, by looking at the area interpretation, and all those rules here, of course, make perfectly sense. Now, another one. Something which is also immediate from the area interpretation is, if you look at this integral, okay, now, if you have some points C between A and B, you can write this as the sum of okay, so this is something which follows from the area interpretation. Okay, so if you have some function if the meaning of this integral here is the area below the function f of x and above the x-axis from a to b, and here you just compute this area as a sum of those two areas, as you see here. It's not a proof, okay, because we have defined the area by this symbol and not the other way around, so this doesn't prove anything. But so in order to prove this, okay, you have to go into the definition, and this is not so easy for this case. Also, this looks very easy. The problem being that it's not necessary that C is one of the endpoints of the intervals which you use in order to subdivide. Okay, so you need also, in order to prove this, you need also that f is continuous. So it's not so easy, but I'm not going into details. Something which is very easy to see from the area interpretation. But if you want to write out all the details, it's not completely trivial. In particular, because you also have to divide cases, because it's not necessary that A is smaller or equal than B. For this, you do not have to necessarily to do this. So this just holds also A must be smaller or equal than B and C between A and B. But this is not necessary for this property to hold. Now, another property which follows much more easy than this one from the definition is if f of x is larger or equal than 0 and A is smaller or equal than B, then the integral from A to B f of x dx is larger or equal than 0. So this is essentially true because this is positive in this case because of this assumption here. And the function is positive, so you can estimate everything by larger or equal than 0, which is 0. Now, if you have two functions, f of x and g of x, and A is larger or equal than B, then what you can do is you look at the new function h of x, which is equal to f of x minus g of x, and this function is larger or equal than 0, so you can apply this one. So you get that the integral over this one is larger or equal than 0, or if you use the rules which we have proved already, the integral of f of x dx is larger or equal than the integral of g of x dx. So this is already a consequence of this one. And from this one, you get another consequence if you know that f of x is larger or equal than m and smaller or equal than capital M, and again, A is smaller or equal than B. You shouldn't forget this one, okay? Because sometimes it's easy to forget about this one, okay? Because if this is the other way around, here the inequality would also change in the other direction. So in this case, you get that if you look at the integral and you just use this property here, so this will be larger or equal than m times b minus a, and smaller equal than m times b minus a. Also, this is something which is clear from the area interpretation. And this is already helpful for some integrals in order to get the lower bound and the upper bound in case you cannot compute the integral. You see, for instance, you could use here those properties in order to prove other properties. For instance, if you look at the integral from a to b f of x dx, okay, so an estimate which is certainly satisfied for f of x is larger or equal than minus the absolute value of f of x, smaller or equal than the absolute value of f of x. Okay, so from this one you get this is and using this property you get this is larger or equal than minus the integral from a to b absolute value of f of x dx, and smaller or equal than the integral from a to b absolute value of f of x dx. And this now in turn implies that the absolute value of the integral a to b f of x dx smaller or equal than the integral a to b absolute value of f of x dx. Okay, so it's quite easy to prove such properties. You see, the only thing you need this here, and you apply what we have already proved. And here, for this one, I should stress it's important that a is smaller or equal than b. Otherwise, it's not necessarily true. It's a common mistake, something which is quite often overlooked. Okay, so those are a few properties we are going to apply in the sequel. As I have explained, the proofs of most properties are easy. You just go to the just use the definition. Okay, we just saw only one property, which is looks very easy. And if you look at the area interpretation, it indeed is a very easy property, but which would not be it's not complicated, but would not be too easy to prove if you just refer to the definition. I hope you remember that last time I told you that if you look at the integral, okay, from the physical point of view, it looks like if you compute the integral of some function f of x and you integrate from some a to x, it looks like that what you get is the antiderivative of the original function. So we saw this already from the physical context, something which is not so apparent if you look at the area interpretation. For instance, let's check this once more for a simple function. So for instance, if you look at this function here, so the difference is now that the upper limit is a variable. Okay, so by the definition, this is the limit, n tends to infinity, and you have the sum. I goes from, let's say, 0 to n minus 1. And then the delta x here in this case is x over n. So what you have is xi squared over n. And then you times x over n. Okay, so if you compute this, so you can take out the x to the cube, which is a constant. And then you have limit n tends to infinity, and the rest is 1 over n, sum I from 0 to n minus 1, I square over n. But this here is, you can, of course, it's easy to compute, but you can write it back as the integral from 0 to 1, t squared dt, and this is something we computed already. So you see what you get is x cubed over 3. Now, indeed, the derivative of this function is this function. So it looks like here something which should be clear from the physical context, that whenever you compute the integral of a continuous function and the upper limit is a variable, what you get is an antiderivative. Okay, so we guess from here that the integral from a to x of some function f of t dt is an antiderivative of f. Okay, maybe I should emphasize once more, it's not so completely clear. This is not so completely clear from the area interpretation, but something which is trivial from the this is something which is trivial from the physical interpretation. So, because if you think about this function is the velocity, okay, if you compute this integral over the velocity dt, this what you should get if the velocity, assume that the velocity is larger or equal than 0, then you have an object which is just moving forward. And if you do this, what you get is the distance traveled. But the distance traveled, so you can say the distance at x. The distance traveled is the antiderivative of the velocity. Okay, so from the physical context, but actually this is something you have to prove, okay, because this is a mathematical object, and you have to prove that this is the same as the distance, which is something which is already defined, which you can measure. So from the physical context, we are easily led to this conjecture. Now, and from the area interpretation, not so immediately clear, but actually, of course, you can find this to be true also as well from the area interpretation. It's just not so natural compared to the physical situation, because so for instance, we have a function here. Let's say this one. Okay. Now, what is the meaning of this here? So maybe let's call this capital F of x. So we fix here some x. Okay. The meaning of this function is the area from here to here. Okay. Now, if we go on to x plus h, and we compute f of x plus h, the meaning of this is the area now not until x, but until x plus h. Okay, so you see from this here that if you compute f of x plus h minus f of x, okay, so this should be roughly, if you look at this picture here, it should be roughly equal to this area here. Okay, and this area you can roughly approximate by f of x times h. Okay, and this will be true if h is getting very small. Okay, because this here f of x times h is, of course, you make an error in approximating this area by this area, but as h is getting larger, smaller and smaller, this approximation should become better and better. And if you divide now everything by h, you see that what you get here in the limit is the derivative of f, and should be equal to f of x. Okay, so this also tells you that intuitively the derivative of this function should be equal to f. Now, I explained to you already last time that okay, if you look at things like this here, it also becomes clear that there is a connection between the area problem and the tangent problem. But before this law was discovered, it was not clear that there is any connection between those two problems. After this was discovered, this result was discovered, okay, it became clear that there is a very close relationship between the theory of integration and the theory of differentiation, and calculus is just a theory of differentiation and integration. So, of course, that there is a connection between those two theories, okay, this is a very important result in calculus. So this is called the fundamental theorem of calculus. Okay, so the fundamental theorem of calculus okay, so assume that let f be continuous on AB, then define a function f of x which is equal to the integral from a to x f of t dt, where x is in the interval ab. Then this function which you get here is differentiable. So f of x is differentiable on AB, and the derivative is equal to f. Okay, so we saw here already the proof idea. We will essentially use the same idea to similar. So we will make this more precise in order to prove it, and then we will get an exact proof. This maybe I should emphasize here another point of looking at this theorem, because when I talked about antiderivatives, I asked several questions concerning antiderivatives, and I told you that later on we are going to solve them. One of the questions was, for which functions does there exist an antiderivative? So the fundamental theorem of calculus also tells us that for continuous functions there is always an antiderivative. You always have an continuous functions always do have an antiderivative. And moreover, this tells you even more. This tells you how to get the antiderivative. Namely, you define this function, and this will be the this will be one antiderivative. Okay, now the proof. Okay, so what we do is we look at f of x plus h minus f of x, as I have done here in the heuristic reason, so minus f of x. Okay, so if you write this down, you have the integral from a to x plus h f of t dt minus the integral from a to x f of t dt. And using one of the rules which I showed you before, this is the integral from x to x plus h f of t dt. Okay, or in other words, if we multiply everything by h, we have here 1 over h. Okay, now we use that the function f of t is continuous on this interval. So this means that the function f of t will be continuous on the interval. So maybe assume that h is larger than 0. Now, f of t is continuous on the closed interval from x to x plus h. So because f of t is continuous, we know there must be absolute maximum and absolute minimum on this interval. Okay, so f of t is continuous on the interval x to x plus h. Okay, so from this we know that f of t takes on an absolute maximum and absolute minimum on this interval. So we know that f of t will be larger equal than f of, let's say, u, and smaller equal than f of v, okay, for all t in this interval here. Okay, and u and v are some suitable for some suitable u and v which are also in this interval. Okay, so this is the extreme value theorem which we use here. Now, this is already quite helpful because we can now plug this in here. So we can use one of the properties we have used before. So you see that 1 over h, the integral from x to x plus h, f of t dt, if you plug this in, is smaller equal than f of v and larger equal than f of u. Okay? So what you get is that this here is larger equal than f of u, smaller equal than f of v. So f of x plus h minus f of x over h is larger equal than f of u and smaller equal than f of v. Okay, so actually everything I have done so far is for h larger than 0, but for h smaller than 0, you can do the same. You have just to be careful about the inequalities. Now so now let h tend to 0 from the right. Okay, if h tends to 0 from the right, of course, because the interval here shrinks, okay, it's tending to x, okay. So u and v are both tending to x, but f is a continuous function, okay. So as h tends to 0, this here will tend to f of x, this here will tend to f of x as well. So this limit exists by the squeezing theorem and is equal to small f of x. And this is what we want to prove. Okay, so if you let h tend to 0, this here will tend to f of x. This here will tend to f of x. Okay, so this limit here, because they are the same, so squeezing theorem, you get that this limit here, as h tends to 0 from the right, exists and is equal to f of x. We get that the limit as h tends to 0 from the right of f of x plus h minus f of x over h is f of x. And similar for the limit from the left. So similar for the limit as h tends to 0 from the left. You will get the same result. So overall, this limit here exists and is equal to f of x. Or in other words, because of definition, the function f is differentiable at the point x, and its derivative is given by small f of x. And this is what we actually wanted to prove. Okay, so any questions to this? As you see in our textbook, the fundamental theorem of calculus, which I have proved so far, is called the first part of the fundamental theorem of calculus. So there's also a second part. Now, before we go on and discuss the second part, we will look at applications or consequences from this theorem. Now, the first thing is that, so for instance, whenever you have something like g of x is equal to the integral from 1 to x ln t dt. Okay, so whenever you have a function which is defined like this, you can immediately know, even so if you cannot compute the integral, because we still do not know how to compute the integral, but even so if you cannot guess how to compute the integral, at least you know that the derivative of this function will be equal to this one. Okay, so whenever this means whenever you define such a function, okay, at least you can you can discuss properties of this function, like where is the function increasing, where is it decreasing, where is it concave upward, where is it concave downward, and so on, because you have access to the derivatives. Okay, so for instance, if you define a function as the integral from 0 to 0 to x 1 over 1 plus t squared dt, and you want to know where is this function, for instance, on which interval is this function concave upward. Okay, then you know that okay, from the fundamental theorem, the derivative of this function is 1 over 1 plus x squared. If we want to discuss concavity behavior, we have to look at the second derivative. Okay, so the derivative of this function is the second derivative of this function is equal to minus. We have here 1 plus x squared, and the inner derivative, which is 2x plus 1. Okay, and for instance, if we want to know, okay, when is this larger or equal than 0, then okay, this is if and only if 2x plus 1 is smaller than 0. This is if and only if x is smaller than 1/2. So if x is smaller than 1/2, this function here will be concave upward. Okay, so this is an important thing. Okay, so whenever we encounter such a function, okay, even so we are not able to compute the integral, okay, we still can discuss properties of this function. Now, you might wonder why is this important, because I seldomly will encounter such functions which are defined by integral. Now, maybe you have learned already in physics that such functions are quite frequent in applications. For instance, one function which you consider in physics is the so-called Fresnel function. So you define a function s of x to be equal to the integral from 0 to x sine pi t square half dt. Okay, so this is a function which is important. Fresnel function. This is a function which is important in optics. Okay, so not only in optics, also design of highways and so on. This function plays an important role. Now, the reason why we define the function like this by integral and do not compute it is because it can be proved that it is not possible to express this here. This, of course, exists because this function is continuous. So this here exists. This has some value, but it's not possible. It can be proved that it's not possible to express it as simple functions of x. So in some sense, it cannot be computed. Okay, but it exists because this function is continuous, and we know that the integral over a continuous function exists. So it exists. But since we cannot express this by some easy functions, we give it a new name. We call it s of x. And this function is important in application. So we have to understand its behavior. But this is easy because from the fundamental theorem, you know that the derivative, the first derivative is just by the function itself. Okay, and from this you can compute the second derivative, and then you can understand. You can try to understand. Okay, how does the graph of the function look like? And this is enough in order to understand. In order to understand some essential properties of this function. So this is one example of a function which is defined as an integral coming from physics. Another example is probability theory. In probability theory, this function, which is called the Gauss error function, plays a very important role. So this function is defined as 2 over the square root of pi integral from 0 to x e to the minus t squared dt. Again, if you look at this function here, you might wonder why not computing the integral. It can be proved, but we are not going to prove this in this lecture. But it can be proved that it's not easy. It's not possible to express it by simple functions. You need much more knowledge on mathematics to understand such proofs. But for this function, it can be proved that this is the case. So since we cannot express this by some known functions, but the value exists for every x, we give it their own name. And as I said, this is called the Gauss error function. So this is a very important function in probability theory. So for instance, if you want to understand, okay, what is the average height of people? Okay, so normally you can study, for instance, you study the average height of the population of some country, and by doing some estimates, you might figure out that the average height is like, I don't know what the average height is in Taiwan, maybe 170 centimeter. So 1.7 meter. If you now want to know, okay, what is the probability that some person lies within is that the height of some person is randomly chosen is larger or equal than 1.65 and smaller equal than 1.75. What you essentially compute is this function. What you essentially need is this function in order to compute such probabilities. So this is a function which plays a very, very important role in probability theory. And even so, we cannot find the easy expression of this function. From the fundamental theorem, we know that the derivative is just 2 over square root of pi e to the minus x squared. So from this information, we can, of course, understand how this function looks like. For instance, we can discuss where is the function increasing, where is the function decreasing, and so on and so forth. Okay, so this is one reason why the fundamental theorem of calculus is important in applications, because in applications we have many functions which are defined as integrals where the upper limit is a variable. Here you have 2 examples. If you are asked to find the derivative of a function like this one, okay, so you're asked to find the derivative of this function here. Here you have x squared. Now, the only trick is to understand that this here is a composite function. Okay, the inner function is x squared. The outer function is the integral from 0 to x cosine square of t dt. Now, in order to compute the derivative, you just use the chain rule. Okay. So for the chain rule, we have we compute the derivative of the outer function evaluated at the inner function. Now, the derivative of the outer function by the fundamental theorem of calculus is cosine square of t evaluated at the inner function. So cosine square of x square. So this was the derivative of the outer function times the derivative of the inner function, which is x squared times 2x. Okay, so it's quite often that such examples occur in the Heu-Kau. Okay, so you should understand how to do this. So you just look at this as a composite function where the outer function is given by a function like this here, by a function defined by integral. Okay, so where you assume the upper limit is a new variable. If you take the derivative, it will be this function here, and the inner function is x squared. So you first the derivative of the outer function, which is this function, evaluated at the inner function times the derivative of the inner function. Maybe it gets even clearer if I write it like this here, f of u. So this is our outer function. Okay, this is our outer function, and this is our inner function. Okay, and now you can write this as d over dx. So obviously you really have a composite function, namely this function here. Okay, and by the chain rule, this is equal to the derivative of the outer function evaluated at the inner function times the derivative of the inner function. Okay, and so once more, the derivative of this one by the fundamental theorem is the cosine square of u evaluated at the inner function. So cosine square of x squared times the derivative of the inner function. Now, there are many variations of this problem. So, for instance, something which is not really related to this, but if you are asked to compute the derivative of this function here, okay. Now, of course, the way you do it, you interchange the limits. Then you have a minus. So this is minus d over dx, and then the integral from 0 to x cosine square of t dt. And here, by using the fundamental theorem, this will be minus the cosine square of x. Okay, so if the variable is in the lower limit, okay, you have to first do exchange, and then you use the fundamental theorem of calculus. If you have something, if you have now to compute the derivative of the integral from x to x square cosine square of t dt. Okay, now I guess most of you have the idea how to do it. You break it into two parts. One is the integral from x to 0 cosine square of t dt plus the integral from 0 to x square cosine square of t dt. Okay, and we saw already the derivative of this function is here, so this is equal to minus the cosine square of x, and the derivative of this function we computed here, so it's cosine square of x squared times 2x. So this is something you should really understand, because I know that from experience that every year in the Heu-Kau there's at least one example, but sometimes we had even up to 5 examples, which are essentially we essentially have to use this idea. Okay, so assume that f is continuous on AB. Then the integral from a to b f of x dx will be equal to f of b minus f of a, where f is an antiderivative of f. Okay, so this is a little bit different to the first part. Okay, maybe I should emphasize what is the difference, because it looks pretty much the same. In the first part, the upper limit was a variable, and we proved that if the upper limit is a variable, what we get here is an antiderivative. This result tells you, okay, that whenever you have an antiderivative, okay, not necessarily the one with the upper limit is a variable, whenever you can find the antiderivative, you can compute the definite integral by evaluating the antiderivative at the upper limit and the lower limit. This you should maybe recognize here that maybe this is completely different to high school. In high school, maybe this was the definition of the integral. Okay, but we went here a completely other direction. So this tells you that actually for computing this complicated limit problem, which we discussed last time and today at the beginning of the lecture, there is an easy way. There is an easy shortcut. Namely, if you can guess the antiderivative of f, you can use the antiderivative in order to compute the definite integral. And you do not have to go into the details of computing the limit. Now, the proof of this result is almost trivial. Okay, so we saw already that g of x, which is defined as the integral from a to x, f of t dt. Okay, we saw already that this is the antiderivative of f. Now, if this f here is another antiderivative, okay, we know that if we have two different antiderivatives, okay, they must be related on some interval. They must be related by a constant. So f of x is equal to g of x plus a constant. Okay, but you see that the integral from a to b. Maybe I should write here something different. So let's here write a c. It doesn't really matter, but okay, just to make this here different. So the integral from a to b, f of x dx. Okay, so you see that this is equal to g of b minus g of a. Okay, by one of the properties of the integral. And now you see, actually you can write this, because the constant here will cancel out because of the minus, so you can write this as f of b minus f of a. Okay, and this proves already the claim. Because the g of x is f of x minus c, you plug this in and the constant cancels. So no matter which antiderivative you're going to use, the result you get here will always be the same. Okay, so this finishes already the proof. Now, as I have explained, this now is the application of this part of the fundamental theorem of calculus is a little bit different from the first part. Namely, the application here is that we get once more a shortcut. We have a shortcut now in order to compute the limit, where we last time spent quite a lot of time to evaluate the limit for just simple functions. For instance, now if you want to compute this integral here, okay, now it's completely trivial. So this part tells you, okay, what you have to do is you have to find, first you have to guess an antiderivative of this function, and this is easy, x cubed over 3, and then you evaluate it. So f of x is equal to x cubed over 3, and then you evaluate it at the upper limit minus the lower limit. So you get the same result as last time. Almost no effort. Okay. Last time the difference to last time was last time we had to go into the limit, we had to compute the limit, and so on. Okay. But this result here tells you there is a much easier way to do such computations. Also for this result, e to the x dx, or was it e to the minus x? I don't remember. E to the minus x. Or was it e to the x? I don't remember. Or e to the minus x. Maybe it was e to the minus x. So last time I think we computed this integral here. Now also here it's very easy. You guess the antiderivative minus e to the minus x. So you see you have to evaluate the antiderivative at the upper limit, which is minus e to the minus 1, and you have to evaluate it minus on the lower limit, which gives you 1. And the same result we proved last time, but with much more effort. You maybe remember this one. Okay, for instance, this was much more complicated by going into the limit, because we had to compute the we had to compute a sum, a quite complicated sum involving signs and so on. And I showed you last time a formula which you get by Maple. But now, once you have this here, the only thing you have to do is you guess an antiderivative, and then you compute it as the antiderivative evaluated at the upper limit minus the lower limit, which is equal to 1. So now this is trivial. Okay. Or also this problem here, so the integral from 1 to 2 dx over x. So also here it's easy to guess an antiderivative, ln of x. And you see now, okay, so this is ln of 2 minus ln of 1, which is ln of 2. And actually, this gives us here, so this is more interesting than the other examples, because this gives us here another way to, so this is, you can say this is a proof that this limit here, 1 over n plus 1 plus and so on plus 1 over n plus n. So if someone gives you this limit and tells you, okay, evaluate this limit, one way to do this is you rewrite this as this to this integral, and then you use this procedure in order to compute this integral. Okay, so this is maybe the most easiest way to evaluate this limit here. So you see, we get here even more. Okay, even by having another way of computing integrals, okay, we have now a way to compute those complicated limits, where last time we have spent quite a lot of time in order to compute them. As I have emphasized, this is not the only way to compute this limit. You can, if you like challenging exercises, you can try to compute this limit without using the theory of integration. Okay, it's not easy, but also not very complicated. I mean, not too complicated. Okay, so from all those examples, okay, you should appreciate this result, and you should understand why this result is called the fundamental theorem of calculus. Because before this result was known, okay, it was quite complicated to compute definite integrals, because essentially the only way which you could take was to write down the limit and to try to evaluate it. Now, after the fundamental theorem of calculus was discovered, so the essential discovery was that there is a close relationship between the area problem and the tangent problem. Suddenly computing integrals was trivial. Okay. Now I understand this is maybe not so surprising for you. The reason being because this was already spoiled in high school. In high school they told you how to do it. Okay, so if in high school they wouldn't have told you that this is the way to compute the integral. Okay, this would be much more surprising now for you that it's so easy to compute these complicated limits, that there is such an easy shortcut around it. You find an example in our textbook which should demonstrate you that, and also this is important for the Heukaus, so sometimes there are examples which use this way of reasoning, and you have to figure out whether where is the mistake. So for instance, if you look at this function here, okay, you see that, okay, it's easy to get antiderivative. So antiderivative is minus 1 over x. Okay, so you evaluate the antiderivative at the upper limit minus 1, so you have minus 4 over 3. Okay. This is an example which shows you that you have to be very careful in order to apply the fundamental theorem of calculus. Namely, you have to check the assumptions because this is a function which is not continuous at x is equal to 0. Okay, so here you are not allowed to use the fundamental theorem of calculus. And indeed, the answer is not minus 4 over 3. This integral, we will later on define such integrals, because actually we haven't defined even this integral, because at 0, this function is not continuous. And we have just defined the integral, strictly speaking, just for continuous functions. Later on, we will extend the definition of the integral to such situations, and then we will see, indeed, in this situation, the integral does not exist, so you are not allowed to do this. So you have to be careful when applying the fundamental theorem of calculus. You have to check whether all the assumptions are satisfied. Now, the reason why in our textbook you find those two parts, why it's separated in those two parts, is because those two parts say something which is quite different. Now, you find in our textbook a summary which combines those two parts in a form which maybe is more easier to memorize. Namely, the first part tells you that if you compute first the integral and then you take the derivative, then you are back to the original function. So this is part 1. And the second part tells you if you compute first the derivative and of some function, call it f, and then you compute the integral, then you are again back to the original function. So in this sense, integration and differentiation are inverse processes. So if you start with a function, you take first the integral with you take first the integral and then take the derivative, you are back to the original function. And if you start with a function and you first take the derivative and then the integral, you are also back to the original function. And in high school, normally integration and differentiation are defined like this, as inverse processes. Okay, but for us, we defined those two operations, taking the derivative and taking and computing the definite integral quite differently. One representing the area problem, the other representing the tangent problem, and the result we proved today tells you that there is a close relationship between those problems, and this close relationship is expressed by those two relations here.